So, hello to everybody. And now we are going to study differential equation in that generality. Up to now we had a long introduction and some philosophy. I think it is really necessary in order to understand what differential equations are. And now we go to the theory, okay, to the theoretical structure of differential equation. So we start by a definition. So what is a differential equation? A differential equation is an identity. Every equation is an identity. Involving an unknown function y and sum of its derivatives. So f of t y prime up to yn, the nth derivative, is equal to 0. Or let me call this equation 1. Okay? Every expression, what is this f? You may wonder, what do I mean? Every expression, every mathematical expression, it can contain sums, product, exponentials, logarithm, tangent, sine, cosine, arctangent, hyperbolic cosine, so whatever you can imagine. Okay? Now, the maximal degree of derivation, so the highest derivative, that appears in 1 is called the order of the ODE. And so as an example, you can imagine whatever you want. So I don't know, y third derivative to the power fourth minus y second plus e to y prime is equal to, and then another function, for instance, cosine of t. This is a very difficult, very strange differential equation. This is random, but more meaningful is the following. We will meet this equation later in an example. Y prime squared plus y squared is equal to 1. And of course, the differential equation we already know. Y prime is equal to alpha y, and so on and so on. Okay, whatever expression you can imagine. But this is not the typical differential equation we will study, because we need a special form, a simpler form, which is given by... So this is, let me say that the order here is 3. This is a third order, this is of the second order, and this is of the first order. Okay, because here the highest derivative is the third, here the highest derivative, it's the first. Okay. No, it's the first order. And here the first order too. Okay. Another definition which is very important, is the following. A differential equation of the following kind. Yn, so the nth derivative of y, is equal to f of t, y prime, up to yn minus 1, is said to be in normal form. What does it mean? It means that the highest derivative that gives the order is isolated from the rest. Okay? So let us see the previous examples here. Let us copy it. Here, you will have that the first one here is not in normal form because the highest derivative here is the third, but it is not isolated from the rest. It has a fourth power here. In order to be in normal form, this should be y3 and stop. So this is not in normal form. In the second example, it is the same because this is a first order differential equation. Here we have y prime, but there is a second power. So it is not in normal form. Otherwise, we should have y prime equal to something. This is not in normal form. Sorry. While the third equation here is in normal form because it is a first order and it is y prime equal to something, and this is in normal form. And very important remark. Please notice that all the equations we studied, so the equation of the falling object, Malthus equation, Fairhouse equation, were all in normal form. So our remark is that we will always study equations in normal form. And another remark, or if you want an example, is the following. The example that I will consider wants to explain you the following thing. That so in some cases a differential equation which is not in normal form is equivalent not to a differential equation in normal form, but to a set of differential equations in normal form. So, not a system. It's only a set. So can give rise to different differential equations. I will explain it by an example. A set of more than one differential equation in normal form. The example is an example that physically, mechanically is extremely important. And so as an example, consider the conservation law to the conservation of the energy for harmonic oscillator. It's a one-dimensional harmonic oscillator. So do you remember? So if y of t is the motion of a harmonic oscillator, I will give you a lecture on that, a sort of extra lecture, because I think it is very useful also for the future. However, now consider y of t is the motion of a harmonic oscillator. Then m divided by 2, where m is the mass of the harmonic oscillator. Harmonic oscillator, think of a spring. Okay, a spring in one direction with elastic constant equal to k. Here is mass m, and we are in one dimension. That means that everything here moves only on a certain straight line that I called y. So m over 2 y prime, which is the velocity of t to the square, plus k over 2 y of t to the square. This is equal to the energy. Okay, this expresses the conservation of energy. For a harmonic oscillator. Why is this expression conservation of the energy? You may say that it is the definition of the energy, but it is the conservation because here there is t. And this holds for every t. But here, in the right-hand side, there is no t. This means that for every t, as time passes, y prime may change, y may change, but this strange combination of the two does never change. It is always equal to E. Of course, when you change the initial condition, you can change E. If you take this spring very far away from the equilibrium point, then the energy rises, so you can vary this value of E. This is true. However, once you leave the mass free to move, this E will be constant. Okay, this is conservation of the energy. Physically, this is conservation of the energy. But mathematically, this is a differential equation because it is an expression, an identity that involves an unknown function y and y prime, a derivative of it. But mathematically, this relationship that I call 2 is a first order differential equation not in normal form. This was the second example I gave you, or the third example, the second example here, with mass equal to 2 and an elastic constant equal to 2. Now, by elementary algebraic passages, we can see that this expression is equivalent to the following. So 2 is equivalent to y prime equals plus minus square root of 2 over m 1 minus k over 2 y squared. Sorry, e, not 1, e. The energy. And these are two, namely, two differential equations in normal form. Okay? Two differential equations in normal form, and I gave you this example in some detail because you will find it again when studying mechanics. And I want you to be ready to understand the 2 points of view on this relationship. Physically, it is very important because this is the conservation of energy, which is something extremely deep in mechanics. But mathematically, you must be ready to see that this is an ordinary differential equation, but it is not in normal form. And probably you have to treat it by splitting in these two possibilities. Okay, I don't want to get in a more detail. And this is all for this example. In our course, we will study only this. We study only this because only for normal form ordinary differential equation there is a powerful theorem, which is the theorem of existence, of uniqueness of the solutions. But before telling you this theorem, what is existence and uniqueness of solution, I must tell you what is a solution. Okay, everybody knows what is a solution. It's a function, you plug it into the ordinary differential equation and it solves it. But I want to define it because there are some details that deserve some attention first, and second, because in the theory of ordinary differential equation there are several notions of solution. Now I will give you the basic one, most basic one, but then there are others. You will meet probably more advanced causes. So the definition I want to give you here is the definition of solution of an ordinary differential equation. So given and let us consider the differential equation not in normal form. Given this ODE, a solution is what? Is a function. Let me call it phi. Phi from I to R, where I as an interval of R such that the same expression, capital F, t, phi of t, phi prime of t, up to the nth derivative of phi of t, is equal to 0 for every t in I. So this is exactly the definition you expect. It may sound some technical because I introduced this phi and so on and so on, but it is really the natural definition. A solution is a function such that if you plug it into the equation, then the equation is satisfied as an identity for every element of the domain of the function of the solution. So it is extremely natural. And of course, if the equation is in normal form, then the solution phi fulfills the following identity. Where is the identity here? So I will write it. So the nth derivative of phi computed in t is, f of t, phi of t, phi prime of t, and then the following derivatives up to phi n minus 1 of t, that is equal to 0. Okay, if the ODE is in normal form, then the solution of phi fulfills this identity for every t in I. This is what we expect. The only remark is the following. Notice that a solution of an ODE is by definition defined on an interval. On an interval I. So in particular, you remember the Verhulst equation where we found the asymptote. So the natural analytic domain, the domain related to the analytic expression, was not an interval, was an interval without a point, the point where the asymptote, the singularity, was present. Okay? And this is not a good domain for a solution of an ordinary differential equation by definition. There is a reason. The reason is that in most cases, ODEs come from modelization of natural phenomena evolve in time without holes at every time they are present. Okay? This is a reason that comes from modelization. So it gives rise to this definition. But there is a thing to pay attention, that it may be that phi1 from I1 to R, I1 is an interval, and phi2 from I2 to R, a solution to the same ordinary differential equation, and I2 is strictly larger than I1. Moreover, for every t in I1, we have that phi1 of t is equal to phi2 of t. What am I writing? I'm writing this So this is phi 1, and phi 2 is the same function, but it is extended. Okay? This is phi 2, and this is the interval I1. And this is the interval I2. So, okay. In this case, phi 2 is said to be a prolongation of phi 1. Of course, by the definition we gave, once you have a solution, this is defined on an interval, but every restriction of this solution to a smaller interval is still a solution. So we are somewhat obliged to give this definition. Phi 2 is a prolongation. This may lead into some confusion, but there is an important result that I will not prove, which is the following. That says, let me be a bit sloppy about the hypothesis. I just want to convey the idea. The important result is the following. Every solution phi to a certain differential equation admits a maximal prolongation which means a prolongation that cannot be further extended. Okay? Sometimes you cannot further extend it because it goes to plus infinity. Think of the asymptote in the example of Helmholtz equation. So, generically, and the following will always deal with maximal solution, namely solutions that cannot be further prolonged. Okay? This is everything for what concerns differential equation. And so let us go to deal with another problem, which is the Cauchy problem. That we already met, because it is the so-called initial value problem. So, the following problem made of nth order differential equation in normal form. Okay, let me write it clearly. This is a nth order differential equation in normal form. Then you add some initial value, like in Malthus' problem, like in the problem of the falling object. So y at some time, at some point, tie naught is equal to y naught, which is real point. But remember that in order to have uniqueness of the solution, we had to impose a one condition in Malthus, which was first order, and two conditions in the falling object, which was second order. So we can imagine that, it is useful to impose as many conditions as large is the order of the differential equation, so we will have to impose n condition from the 0th derivative to the function up to the n minus 1 derivative, which is y n minus 1 in R. So this problem made in this way, there is an nth order ODE normal form, and then there are n conditions on y prime up to y n minus 1, always at the same point t naught. This is very important, the same point. So the following problem, a problem formulated like that, is called a Cauchy problem, or an initial value problem. Okay. So the complex of this additional conditions outside of the differential equations, is called initial data. These are n initial data. Okay. So this problem is a Cauchy problem. Now let me give a remark before giving you the very important theorem, but the remark. The remark says that generically means if everything is honest in some sense. So generically, a differential equation admits infinitely many solutions, we already know. Okay, differential equation has infinitely many solutions, but there are some pathologic example, like conservation energy y prime squared plus y squared is equal to 0, for instance. This only admits y t is equal to y prime of t is equal to 0 for every t now. However, and this is the very important theorem. This is called the theorem of existence and uniqueness. Of the solution to a Cauchy problem. The theorem is the following. Consider the Cauchy problem, like before, this is the Cauchy problem. Like before, where f satisfies first if f is an n variable functions. What is an n variable function? Okay, we did not study in analysis 1 this, but now it is necessary to understand what is. It is a function f from R n to R, so that if you take n numbers, and let me call them t, z, z1 up to zn minus 1, and then it goes to a single number, then this f is continuous. What does continuity mean for an n variable functions? Let me be extremely sloppy and vague, intuitive. If you go close to, if you are, for instance, in the two-dimensional space and you get close to one point, t naught, z naught, the function on the point of the path you take to go there has a limit that coincides with value of f at the point, very intuitively. Okay, I don't want to introduce continuity in an n-variable function. It is really analogous to one variable function, but there are some things to take care of. You will see it at analysis 2. Okay, and this is, now I want to go to intuition and also to honesty. You will not have strange functions at the exam. Second, this is more difficult. Fix all variables t, z up to z n minus 1 except one. For instance, the j's, say z j's, and differentiate with respect to zj. So, namely, define a function psi of the only zj, which is given by f t z z1 up to zj minus 1, and then you have zj plus 1, and then zn minus 1, and all the variables except the j's, except zj, are fixed. These are fixed, and these are fixed. Then differentiate with respect to zj, and then you have then psi prime in Zj is bounded by C for every value of Zj and independently of T, Z1, Z, Z2, up to Zn minus 1. This is quite technical. I'm just saying that we will see it in a strange example. We are just saying that here the growth of this f that defines the differential equation of the Cauchy problem is controlled, cannot explode. This cannot grow too fast in any variable y. Not t. T is not important here, but in any variable y. Okay, this is technical, but it is less technical than the true hypothesis, okay? I'm doing just that. Then, if these two hypotheses on F are fulfilled, then the solution to the Cauchy problem is unique. And this is the theoretical version of what we already saw. We already saw this uniqueness when fixing initial conditions for differential equations, for Malthus and also for Newton's equation. We really did not enter into detail for Verhulst equation, but this is true also for Verhulst equation. This is a very important theorem. Why is it a very important theorem? Because when you have a model or physical or biological of a natural phenomenon, you want that this natural phenomenon evolves in a unique way. You're able to describe it. And really the fundament, the ground, in order to have this very important result is this theorem. So if you don't understand this, then stop video, go back and listen to it again and try to reason by yourself and take books and take other videos and so on. You have to understand this fact. This is extremely important. This is the heart of the theory of differential equations. Without this result, it will be meaningless to build up models with differential equations. Okay? So, first comment. The first comment is the following. In examples on Malthus and Newton's law, we directly verified that by imposing initial conditions, only one solution was selected. And now there is an example that goes against this theorem, does not deny this theorem, but we have to give up a condition, and then we see that the theorem, of course, crashes. Lack of uniqueness, and it is a typical example, which is also called pianos. Piano was a mathematician from Turin, from Cuneo indeed, but he worked in Turin. Pianos, mustache or pencil. And this is the Cauchy problem we are considering. So consider the Cauchy problem as follows. Y prime is equal to y to the power 2/3. Y of 0 is equal to 0. So notice that here, this is of the type we showed before, and f of y is equal to y to the power 2/3. And so f prime of y is equal to this 2/3 y minus third, and which is not bounded around 0. So here we are in the realm, we are outside the realm of the theorem of existence and uniqueness. So let us see first this equation admits separation of variables So as a first step, we look for constant solution, like for Verhulst, constant solution y of t is equal to 0, because it is the 0 of f. F of y is equal to 0. So, and this solves the Cauchy problem. But then you go with the separation of variable. On the other hand, by separating the variables, you get y prime times y minus 2/3 is equal to 1. Then integrate. Here you have dy. Y minus 2/3 is equal to t plus c. And then this is 3y to the power 1/3. So you have y to the 1/3 is equal to t plus c over 3. And this is equal, this implies y is equal to t plus c to the cube over 27. And then imposing the initial condition zero is equal to y of 0. This implies that c here must be equal to 0. And then y of t is equal to t cubed over 27. And this again fulfills the initial data and solves the ODE. So it solves the Cauchy problem too. So this Cauchy problem has two solutions. One is t equal to 0. So, sorry, y equal to 0. The other is y equal to t. Sorry, there is a horizontal inflection point here. So t cubed over 27. But there are infinitely many other solutions to the Cauchy problem. Not to the differential equation, this will be normal, but to the very Cauchy problem. Infinitely many. So the exercise I give you is find them. And this is the end of this lecture, the theoretical lecture on differential equation. But it is very important. It is theoretical, but it is very important to understand what you are doing. So don't be lazy. Listen to this lecture. If you don't understand the way I explain the thing, look in books, look for more information in other videos and so on. Okay? From the next video, we will try to solve explicitly differential equation. We will go to the 3 huge categories of differential equation I announced at the beginning of these topics. Bye-bye.